Good morning, everyone. This is Chris with the Ancient Scholars. So I just want to go ahead and talk a little bit more about thermodynamics, and hopefully I'll be able to put out several videos on that eventually. Just kind of depending on kind of how busy I am. I've actually been just exceptionally busy, and the only time I really have to do these videos is at really early in the morning before classes start, and then the rest of my day's booked until usually 10 or 11 at night. So I do sort of kind of want to apologize for kind of losing some of my momentum on the videos, but life is just exceptionally busy right now. I do try to get at least a video or two out a week if I can, however. Yeah, I've had some issues with the iOS update, and some of the in-class videos that I've been doing, recording off of a program called AudioNote, it's just been exceptionally difficult to try to get those files turned into a format that YouTube could recognize. That's actually one of the limitations of filming, with my iPad, is that my iPad still doesn't realize that YouTube allows me to upload videos longer than 10 or 15 minutes. So I've had some technical issues as well, in addition to time constraints. But I'm still trying to hang in there and get videos out to you guys. So thanks for watching, and definitely thank you for all the comments. So today I'm going to talk a little bit about thermodynamics and a little bit about where thermodynamics perhaps breaks down, and not necessarily breaks down, but I just want to emphasize the subtlety of thermodynamics and really where thermodynamics has its application. And it should become fairly obvious. So you remember I talked about the laws, the four laws, the zeroth, first, second, third law of thermodynamics, and I had mentioned something about the concept of energy, and that in a thermodynamic sense, energy is neither created nor destroyed. We just basically, energy can take on different forms, and there are a lot of forms of energy that are not particularly efficient. We can't really get the kind of work that we'd like to. Heat, for example, is one of those forms of energy that isn't particularly efficient, and we have to do a lot of things to really get any work out of that. And that's kind of the whole concept of thermodynamics, is to how can we get work out of systems, and how can we optimize efficiency out of systems. That's where thermodynamics really came about in the Industrial Revolution, where we had the internal combustion engine had just been developed. We had steam engines and trains and things like that, and we were trying to figure out how to make this stuff work. And I'd said that energy is not created nor destroyed. It's just kind of basically there are different forms of it, and it just kind of gets formed into one form or another. Well, what I'm going to do today is I'm going to give you an example of where this can potentially break down, or does it really break down? And the example that I give, or that I will give, is something called the microwave background radiation. So what I'm going to do is I just want to go ahead and explain what that is if you guys have never heard of that. It's the microwave background. Okay, so the microwave background radiation. Well, the current theory of the universe, or one of the leading theories, is called the Big Bang. Everybody's probably heard of that. The Big Bang. And I think it's somewhat misleading, and a lot of people have this thought in their head that everything blew up and there was this big massive explosion, and I don't really know what happened, but what we theorize is that at some point in the early creation of the universe, when the universe came about, however, obviously we don't know exactly what happened at time zero, and that's probably better described by religion. You can kind of bring religion in and describe all that. But we certainly don't have any real quantitative way of looking at what happened before that. But at some point in the early universe, there was just a rapid expansion of space and time. That the universe at all points just rapidly expanded. and we had stuff going everywhere pretty much. And that's still expanding to this day. Obviously, I don't think it's probably expanding as fast, but we still have space and time, or space rather, literally expanding. And in the early universe, matter and mass and all that wasn't like it is today. It's a lot cooler now. But basically, in the early universe, basically it was just kind of a soup of energy. I eventually things cooled down to where protons and electrons could come together, and I could have atoms. But before that, these really high energies, these real high temperatures, it was just kind of a soup of all these particles and stuff. And obviously, there's a lot of energy and a lot of light and photons, and because everything was so compact, so massive, so thick and soupy, if you want to look at it that way, we really didn't, photons really couldn't go anywhere because they didn't have very far to go, and they'd run into whatever particles and stuff. Well, as the universe kind of cooled off and became more transparent, if you will, we had more expansion, it became a little more transparent. The photons, light wasn't smashing into stuff as much, and then light could be given off. And so that's why at some point, if we keep looking further and further back, we're going to get to a point where we can't see any further back because it was opaque. Light simply ran into stuff. Well, what we can see, however, if you keep looking further and further back, is we can see the light from the early universe. And when we look at this light from the early universe, we notice something very interesting. Because the universe has been kind of expanding everywhere. It's expanding everywhere. A light, a photon, and I'll draw that in blue, from the early universe. Let's say that light was, very high energy, very very small wavelength photon. Okay, in the early universe. Well, because the universe has been expanding and expanding and expanding, again, it's not the photon, it's not the light itself, it's the universe, it's the actual space itself expanding, What happens is that photon travels toward us, our little planet here, because, space is literally expanding. The photon is the wavelength, basically, if you want to look at that, in essence, is being pulled out, and it has started out kind of a real high energy, real small wavelength light. Well, as time has gone on, as expansion has occurred, the wavelength has kind of been stretched out, if you want to look at it that way, and has become shifted into the red spectrum. Started out real high energy. It's been shifted into the red and the radio, and ultimately into the microwave. So the light that we see from the earliest universe, this background of the earliest universe, is called the microwave background radiation, and we don't actually see it as it was in the early, it was these really high energy photons, but because space has literally expanded, what's getting to us is not these real high energy photons, because it's basically been stretched out, if you want to look at it that way. It's actually these really low wavelength, low energy light in the form of microwaves. Okay, and that's what the microwave background is. It's actually very cold. I believe it's about 3 degrees Kelvin, plus or minus a little bit. So it's really cold, very low energy. But at one time, when those photons were initially emitted, they were very high energy. And I'll kind of, in the next video, we'll talk about kind of how that's, or why that might be significant.